start a session on its transportation, storage, and infrastructure. The topic is long duration energy storage solutions. It's a very, very emerging topic. So a lot of diversified thoughts are there. We are having very eminent speakers in the forum who will be who has done a lot of research and will be presenting their papers on various themes. So now, say in the world, methane gas hydration or cavern construction, it's all unique models in which they will be speaking. All the 5 speakers will be speaking on unique models. So we first invite Mr. Ram, Superintending Chemist from ONGC, to present his hard work and research of 6 years on methane gas hydrate formation experiments in which he is in, and about the transportation challenges. Over to Mr. Ram. Your time starts now, so you will be given 14 minutes. So please stick to the time, and
Sure.
all the very best.
Good afternoon, respected chair and my industry colleagues and friends. Myself, Het Ram. I'm from ONGC and I'm working at GHRTC. So I'm working at GHRTC, Gas Hydrate Research and Technology Center, ONGC, Mumbai, Panvel. Our team carried out the study on methane gas hydrate formation in the presence of green chemical as an thermodynamic gas hydrate formation promoter. So this is the title of my study. Overview of my presentation is first I will talk about gas hydrates and their applications. After that, promoter chemical for gas hydrate formation promotion, and I will then talk about experimental setup and results, and after that, conclusion. So firstly, what are gas hydrates? Gas hydrates are ice-like structures. They are more thermodynamically stable than ice, and they are formed under high pressure and low temperature regimes. And gas hydrates can be formed of gases at given particular setup of high pressure and low temperature regime. So this is the basic structure of methane gas hydrate, in which the center is of methane gas molecule and surrounded by water molecules under high pressure and low temperature conditions. And the density of gas encapsulated in the gas hydrates is huge. 1 unit of hydrates can contain 164 units of gas at standard temperature and pressure, and 0.8 unit of water. So this is the phase diagram of methane gas hydrates given in the right side of the slide. So now I will talk about the application of gas hydrates. The enigmatic nature of the gas hydrate is that they are more stable than ice, but they can be used for various applications, possible applications, not commercially viable till now. So firstly, we can hydrates as a proposed, we can think about as an energy resource. They are they occur naturally in marine setup and permafrost areas. So firstly, we can see them as in technologies. As in technology, see them as an energy resource. Secondly, one is flow assurance. In oil and gas industries, mostly we encounter the gas hydrate stability zone for the pipe, for the oil and gas pipes. So there we can use inhibitors for the flow assurance. And third one is the gas transportation and storage, in which we can store gas as an energy in the form of gas hydrates. The fourth one is CO2 sequestration. We can store CO2 in gas hydrate formations. And fifth one is the desalination of water. Gas hydrate technology can be used for the desalination of water. And after dissociation of gas, we can get pure water. So today's main topic is gas transportation and storage. I will be talking about the gas transportation and storage part. The next one, gas transportation and storage. Here I have compared CNG, LNG, not LNG and MGH for the energy density. 1 unit of CNG is 25% of energy density compared to gasoline, and 1 unit of LNG is compared to 60% of energy density of gasoline. And in case of methane gas hydrates, the energy density is 100 to 200% of gasoline. So I'm giving just overview of the energy density which I'm talking about. So as in gas transportation, storage and transportation solutions, I have mentioned the CNG advantages and disadvantages, and also the compression ratio of methane gas hydrate compared to LNG. As we know, CNG is low cost, widely available, and but the energy density is very low. And for LNG, high energy density, long distance transportation, but the facilities are very expensive. And in case of methane gas hydrate, very high energy density and environmental friendly. But the commercial viability is not ascertained yet. So in my study, I will be showing next what we are proposing for that. And for the compression ratio, LNG from gaseous to liquid, the compression ratio is 600 times at minus 162 degree and 0.1 MPa. And for gas hydrates, we are converting gas from gaseous state to solid state. And here the compression ratio is 1600 to 1800 times under the pressure condition of 8 to 13 MPa, and temperature is between 10 to 15 degrees Celsius. While screening the chemical for gas hydrate formation promotion, first I will talk about the chemistry part of the gas hydrate formation. Hydrate formation usually occurs when the water molecules forms the cavity simultaneously and encapsulate the gas molecule and forms a stable lattice. And for that, to form more stable lattice, we have used the thermodynamic chemical for the gas hydrate formation promotion. So they can give more stability to lattice or cage-like structure of methane gas hydrate formation. So selection potential for this green chemical was that it should increase significantly the formation temperature of methane gas hydrate, or either reduce the pressure of the formation of methane gas hydrate, and should not be hazardous. So green chemical as a thermodynamic hydrate formation, here we use cyclopentyl methyl ether, and we have compared it with tetrahydrofuran and 2-methyl tetrahydrofuran. So compared to THF and 2-methyl THF, it has the low miscibility, and it also produces low oxides, peroxides, which are dangerous for the processes. And it is also a green chemical and a low heat of vaporization for the easy handling of the energy. So we carried out the gas hydrate formation, methane gas hydrate formation in the lab. This is the high pressure reactor cell in which we can pressurize gases up to 250 degrees Celsius, and the cooling heating unit is there. And the right side of the slide, there is this pictorial representation of hydrate cell system we use for methane gas hydrate formation. Results and discussions. Here we have found methane gas hydrate in pure distilled water. This is for the reference. We started from 2000 psi and 20 degrees Celsius, and we stepwise lower the temperature of the hydrate cell, and we lowered it up to 2 degrees Celsius. And hydrates were formed. I think the hydrate formation, why it is conundrum for this energy storage, because the induction time and the growth part, the time between them is very high. So this is there. I have mentioned there. I have mentioned there P equilibrium and T equilibrium, which is the onset of the phase diagram for methane gas hydrate formation. And the upper one curve is the methane gas hydrate formation, which cooling, we are cooling downward. And after that, we are heating so that hydrates are dissociating. So lower one is methane gas hydrate dissociation curve, and upper one is the methane gas hydrate formation curve. So this experiment we took as a reference for our green chemical. So we carried out many experiments. So I have taken two experiment with 2.5 and 5% volume by volume concentration of cyclopentyl methyl ether. So as you can see, the significant increase in the growth of methane gas hydrate formation and as well as phase diagram has shifted to higher temperatures. So next, while using the this green chemical as a methane gas hydrate formation promoter, these are the graphs. First one is for the induction time. First one is for the induction time, and second one is for the equilibrium temperature promotion towards higher temperatures. So in first one, the induction time for the methane gas hydrate formation in the distilled water, the induction time was 420 minutes. And while using the 2.5% volume by volume methane gas hydrate formation promoter, the induction time was reduced to 372 minutes. And for 5% volume by volume, it was reduced to 312 minutes. And likewise, the equilibrium temperature for the methane gas hydrate formation, significant increase in formation temperature was observed. So here we can see the in pure distilled water, the equilibrium onset of the equilibrium was 15.8 degrees Celsius, and while using 2.5% volume by volume concentration of green chemical in the solution water, the equilibrium temperature increased to 16.9 degrees Celsius, and for 5% volume by volume concentration of chemical promoter, the equilibrium temperature shifted to 17.7 degrees Celsius. So this is the significant increase in the formation temperatures of methane gas hydrate formation. So this is the conclusion, significant increase in methane gas hydrate formation temperature were observed while carrying out the experiment using green chemical. And the identified chemical was green. And also for this study, we got the patent from Intellectual Property India. So this is the conclusion. Any question, please?
Thanks, Ram. It's a very insightful experiment and presentation. And basically, it's a very emerging field. And how we are going to do with green chemicals and promoters, it's very insightful. Thanks a lot.
Thank you, sir.
Now we are moving ahead with the next topic in long duration energy storage solutions. We all know that caverns is one of the emerging growing fields. Lot of challenges are there in using a rock as a tunnel and use it as a cavern. Now we invite Mr. Ramana Murthy, DGM-LPG projects, HPCL, to present on the challenges which he has faced in cavern construction for hydrocarbon storage. Over to Mr. Ramana Murthy, please.
Good afternoon all. I am Ramana Murthy, DGM-LPG projects, presently heading the cavern construction for LPG storage at Bangalore, Karnataka. Basically, this is a new concept, though it has been 15 years that the first LPG cavern was made in India, in Visakhapatnam. This is the second cavern that is coming up, made by an Indian OMC with Indian PMC. The EIL is the PMC for the project, with backup consultancy from Geostock, France. And this is a 80,000 metric ton cavern storage. Yeah. So for those who are new to the concept, cavern storage is a huge storage space that is created in the hard rock at a depth required as per the design pressure and temperature for storage of either crude oil or LPG or whatever. Even natural gas caverns are coming up, not in India. There are 4 types of cavern storage. One is salt leach cavern. The second is depleted aquifers. The third is disused mines, like wherever the mining activity is over, you have a tunnels already created that can be used for product storage. And the fourth one is mined caverns. Mined cavern is you are creating a space by drilling and blasting method, and you are creating a tunnel in the earth crust, in hard rock that is. And in this presentation, we are going to cover that mined cavern storage. These are the details of cavern storages existing in India as of date. We have an LPG cavern which is in operation for the past 15 years. It is a 60,000 metric ton cavern storage. The second one is a crude oil cavern storage. Two more crude oil cavern storages were made by ISPRL. These are almost 10 times higher in volume compared to an LPG storage. Presently, we are making a LPG cavern storage at Mangalore. It is 80,000 metric ton single storage space. Incidentally, that will be the highest LPG storage in India. These are the advantages of mined rock cavern. The product is stored at a depth. In our case, it is at 150 meters below the ground level. In the hard rock, the tunnel is being made. And for information, the storage space doesn't have any metallic container. We are making a hollow space, that is, we are making a tunnel at a depth of 150 meters, and the water table will be acting as the container. I will explain you in the next slide. So basically, these are the advantages you have. It is cost economic to make. It is very cost economic to maintain. You don't waste any space. You have the storage at a depth, and you can make all your above ground facilities above the storage space. You don't lose any land for making the storage space. Unlike in cryogenic storage or above ground mounted vessels, you need space to site the facilities. Here you have the storage space at the bottom, and you can have your above ground facilities at the top. No wastage of space. And this is the safest mode of storage. You have the product at a depth of 150 meters. External fires will not affect that. Neither the earthquakes or the storms, nothing will happen. So it is the safest mode known for product storage. This is the storage principle. Two basic requirements are there. One is the rock quality. The rock should be having minimum fissures, the cracks. The quality of the rock is very important. The second requirement is presence of water table. Water is the one which acts as the container. Basically, the principle is wherever you have water table, you make a hollow space there. What will happen? Water tries to occupy that space. So we are creating a tunnel at a depth of 150 meters in hard rock where water table is there. So eventually water tries to come in. And as you know, every 10 meters of water table, it is equal to 1 kg of static head. It's the thumb rule. So I go 10 meters deep, make my tunnel, I get 1 kg of water pressure. I go 150 meters, I am having a 15 kgs of water table trying to come into the space I have created for LPG storage. Getting it? All right. So this is the containment principle. So why I have to go up to 150 kgs? Because my design pressure requirement is 8 kgs for LPG for that design temperature. So I have kept a margin of under 7 kgs and I have gone up to 150 meters. So at 150 meters, my product can go only up to 8 kgs maximum, whereas I have 15 kgs of water table trying to come in. This is in simple. This is the technique behind this cavern storage. And this is the isometric view of the cavern. Yeah. Here, I'll just explain you this orange color tunnels. These are the two storage cavern galleries at 150 meters deep, interconnected by tunnels. So it eventually makes a single storage space of 80,000 metric ton. This LPG space is separated from external atmosphere by a concrete plug. This is at 150 meters depth. There is a vertical tunnel made wherein the cavern equipment, all the LPG pumps, seepage water pumps, the measurement lines, all the equipment will be in this vertical shaft. This shaft is connected to the storage space by one liquid connection and one vapor connection at the top. There is one more concrete plug in this operation shaft which will be segregating the LPG space from the external atmosphere. And this particular tunnel, this is called access tunnel. This is the ground level. From here, we are making a tunnel into the hard rock. This is a sloping tunnel. From ground level, I have excavated the earth. I have reached the hard rock level, and from here the tunnel is going in a sloping manner at 1:8 up to the storage cavern, and the excavation is done. Basically, the access tunnel is a construction purpose tunnel because all my equipment will be going through that. That is a 8 meter by 8 meter tunnel. The construction equipment will be going to the cavern space. The drilling and blasting is done with explosives. The hard rock is carried by trucks along this tunnel. And I have two horizontal blue color tunnels. These are called water galleries. Basically, these will be ensuring that the rock is always maintained with water. The water saturation is there in the hard rock during operation. And this is the schematic. It's basically from the vessel, the LPG will be coming into the cavern. From here, I have LPG pumps and water pumps. The purpose of water pumps is, as I told you, the water tries to come into the LPG space. But it's not like gushing inside. Through the small pores of the rock, it will be trying to come in. The rock is having the pressure at 15 kgs because it is at 150 meters depth. But the water will be coming in at a very low rate of maybe around 20 kl or 30 kl per hour. But ultimately, the water has to be taken out. Otherwise, one day, the cavern space will be completely filled up with water. No space for LPG storage. So there will be separate water pumps at the bottom that will be pumping out only water. How it can pump only water? As you know, LPG and water are immiscible. Water is heavier than LPG. It settles at the bottom. So the water pumps are at the bottom in water space, and the LPG pumps are at the top. That will be pumping only LPG. And this is the photograph of the access tunnel. And this is how the operation shaft looks like. This is the photograph taken. Presently, we are at 120 meters deep. This is a vertical tunnel. This shot is taken from the bottom. This is a 120 meters deep tunnel. I'll just tell you how the rock blasting is done. The sequence is like, this machine is called the jumbo machine. This is the heart of the construction. It will be having two drill heads. We will be making around 150 meters. This is a access tunnel. Size is 8 meters by 9 meters. First the marking is done. Then the drilling is made around 150 meters, 4 meter deep. Drill holes are made with this machine. Then the explosive is charged. Around 300 kgs of explosive is charged into those holes. The lead wires are taken out. The manpower is evacuated. The machinery is taken out. The blast is done. And this is what the hard rock after the blast. The whole hard rock is removed. And after the blast, every blast we will be getting a pull of 3 meters. The advancement is around 3 meters. Daily we do some 2 to 3 blasts every day. And after the blasting is done, the geologist team goes and they will be mapping the fissures. I mean, how the cracks are propagating, because it is very important that no rock fall should be there. Neither the fault zones, two fault zones are meeting. There will be a conical rock formation which may fall. So based on the geologist's report, we will be doing the protective measures. Like this is you can see on the sides, you have the shotcrete. This is a 100 mm thick shotcrete, concrete mixed with metallic fibers. The lining is given because in the subsequent blast, the small rock fall should not be there on the workman. So it is only for the protection during the construction. It doesn't have any role to play during operation. And you can see the rock bolt is done. These are 4 meter deep rock bolts which are drilled and fixed with concrete into the hard rock. Any small boulders, they are fixed to the parent rock. And the next cycle continues. This is the blasting sequence that happens. Since we are handling explosives, the requirement of safety plays a very big role in the construction. Prevention of rockfall is very, very important. And there is a scaling operation. After the blast is taken, excavators will be going and scratching the roof of the tunnel as well as the face, so that any loose rock that will be taken out. Then the explosives blasting has to be executed by a PESO authorized shot firer. He is licensed by name. License will be carrying his name. Only he is authorized to carry out the blast. And there is vibration monitoring is done with the help of vibration sensors. Normally a building it can withstand up to 15 mm per second, but we are only at 1/10 of the vibrations that are allowed. And we have rock strata movement. There are optical monitors that are fixed onto the tunnel so that periodically the readings are taken. Any movement in the rock, that optical sensors, that will be giving an indication that there is a movement in the rock and the tunnel may collapse some point of time. So the periodic readings are taken. This is a regular exercise. And we have mitigation of fumes and dust. A lot of fumes and dust are generated in the blasting operation. We have big ventilation fans that will be taking out the dust and pumping in fresh air. And we have the access control is very important because people going in and coming out, that has to be cut, because every blast we have to ensure that no one is inside the tunnel. So that is done with a QR based access control system. Any point of time with the click of a button we can know no one is there in the tunnel or how many people are there in the tunnel. And we have achieved 3 million safe man hours till date, not a single incident in the last 2 years of construction period. And these are the challenges what we have faced. There is we have encountered soil collapse. There is a cover of 15-meter soil before we touch the hard rock. During the course of construction, a portion of the soil has come down because we have encountered a clay soil which has not reflected in our investigative boreholes. What has happened is once we have dug the soil, the clay portion has come out and the whole side slope has collapsed. And a special solution has been given by Engineers India Limited or PMC. Special self-drilling anchor bolts, 15 meters long, which are used in Himalayan range normally. So those bolts were employed in our project, and we could overcome that problem. Then high water seepage due to the joints present, due to the dikes and joints present in the rock. We have engaged various techniques, including multi-stage grouting. Then also in the vertical shaft, when we had the huge seepage, we have engaged chemical grouting as a special case. Normally caverns, they don't use chemical grouting. First time we have used in our cavern. And also the presence of shear zones, it makes the tunnel unstable. The crown may collapse. So special protective measures like steel ribs were used, or some lattice girders. These are all the construction protections that are done in caverns, the tunneling part. So those were engaged as a protective measures. And these are the photographs, like this is the metallic girder. So these are called metallic ribs. This is given as because when we started the access tunnel, this is only 1.2 meters rock line. So as we progress, there is a chance that it may collapse. 1.2 meters is too thin. So these are the metallic girders which are put as protection, and the further blasting is taken. And this is a lattice girder. You can see the lattice girder. This is the reinforcement rods put, and it is covered with concrete. This gives additional protection to the tunnel stability. And these are the optical targets. What I have told, the tunnel is fixed with these optical targets, and the 3D position is marked every week. Any movement in this optical targets gives an indication that the tunnel is having some stability issues. And this being the new technology, this being for the first time an OMC is doing, it was a learning experience, but at the same time we had never had any incident in the construction. Probably in the next 6 months we are going to complete the project, and definitely this is going to add to the strength of the Indian petroleum industry. Thank you.
Thanks a lot, Mr. Ramana Murthy. Very wonderful presentation, and you completed on dot. Actually, in such an interesting topic, lot of experience sharing on challenges on cavern, particularly the way in which you have put on the principles of LPG at 8 kg and water at 15 kg, how naturally your hydrostatic pressure is acting. It was very wonderful, and my compliments for storing LPG in a cavern. So that's one of the unique use cases which you have presented. All the best.
Thank you.
Thank you.
Thank you all.
Now we are going into another very challenging and diversified topic, where she says heat makes up for 2/3 of industry's energy demand. She is welcome Abheeti Goyal, researcher, Shell India Private Limited. She will be talking about integrated energy solutions, energy storage solutions. Over to you, Abheeti. All the best.
Thank you, sir. So a bit of change of gears, right? We've been talking about, my previous presenters talked about LNG storage and all that. I'm talking more about the thermal energy storage, right? It is a topic, in my opinion, that needs a lot of attention, which it is not getting as of now. But before I start the presentation, there are two things that I must do. Of course, I am presenting the presentation, but actually I'm representing a big team. As you can see, the names in the black line are my co-authors, but of course the list is not exhaustive. We have a big team in Shell which works extensively on this, and I'd like to start by thanking all of them who may or may not be present here in the room today. And second topic is actually for all of you. It's a cautionary note that is must for us, which basically says in a very short, tiny print that please do not buy or sell Shell shares based on what I tell you today. You will be solely responsible for your investment. So having said that, I'll move to the presentation. In the last 2 days, whatever we have heard in the India Energy Week, I think there are many keywords that we heard. And out of those keywords, for me, there are 4 that are major. One is energy security or reliability. The second one is decarbonization. The third, electrification. And lastly, and most importantly, I guess, in making all of this reality would be affordability, right? So all these things together, we need a multi-pronged approach, and that's what you see on the slide, that you have to go through multiple stages in order to achieve decarbonization while maintaining reliability of energy supply and affordability. Out of the many solutions that you see on the slide, energy efficiency, CCUS, hydrogen, and of course biofuels and all that, the topic that I want to cover today is electrification of heat or heat decarbonization. And why heat, right? Why heat? Because heat actually contributes 2/3 of the industrial energy demand. As of now, we are supplying it through different forms of energy, converting into heat at the last very moment, where we store energy in some other form and then provide heat at the very end. But how about we store the heat in the form of heat? Not for the purpose of avoiding conversion multiple times, but also because of the efficiency that it gains. If you have heat stored in the form of heat, you will have an efficiency, ideally even 100% if you can isolate it from the surrounding, but in practice, at least between 90 to 95%. And if you convert that heat into electricity, that leads to about 30 to 40% efficiency. So by doing the reverse and storing heat only in the form of heat, you actually save at least 60% of your round trip efficiency. Before going further into what kind of thermal energy storage, this is the general idea of how long duration energy storage is going to evolve. Right? This is the council that's at a global level, and I would like you to focus on the right-hand side of the screen and the graph that is in green. What it basically says is that long duration energy storage typically meant storing for generation of power, for the purpose of power at the end of the day. But what it basically tells you from the line that's dividing the graph into the 135% increase that's expected by 2040 is purely in the form of thermal energy storage, not for the conversion of power later, to be utilized as heat itself. And the dark green band just below that dividing line is only that percentage that would be used later to convert into power. So you can see you'll store energy in the form of heat tremendously, about 140% increase than what we are anticipating for power LDSE. But out of that, about 135% increase is solely in the form of heat storage. Of course, this is the global scenario, but what about India, right? Since we are in India and we're talking at the India Energy Week, it's must that we look at this pie chart. There are 2 pie charts that you see. One is the installed capacity as of today, let's say, and the gross generation. So what I'm trying to show you in these 2 graphs, 2 pie charts basically, is one, what is the capacity installed versus how it's utilized, how much it is being consumed, and what's the distribution of that energy mix that you end up consuming, not the distribution that is installed on ground. And as you see, even today, as of today, we are 50-50 roughly in terms of coal versus the rest of the energy forms in terms of capacity, installed capacity. But in terms of utilization of that capacity, we are way far off. So you can see about 70% of the energy that we consume today in India is coming from coal, in spite of the fact that your capacity is actually balanced in a way. And that's because of the point of reliability and affordability. Even in 2030, that's the projection from the CEA, which is an Indian authority. Even in 2030, the expected distribution of the utilization still remains more than 50% estimation for coal. And that again to the point of affordability and reliability. Maybe solar would become more and more affordable, but is it available throughout the day for it to be reliable? One thing additional to reliability is the cost of it. So this is an example of how electricity prices on an average fluctuated over time in India last year. So every month you have an average, that is the green line, average electricity price in Indian currency per kilowatt hour, rupee. And it also shows you the distribution, in the sense what was the maximum, what was the minimum. And I would like you to focus on the extreme case, which is for March 2022, right? Here the green line is somewhere in between, but the lowest is about 3 rupees per kilowatt hour and the highest is about 17.5. So you see the band at which we fluctuate. And how does it fluctuate? It's not like it's constant for the whole month. It fluctuates actually in reality every minute or every 5 minutes. But in the day ahead market, that is you get to know, say today, what would be the price hourly for the next 24 hours, and you optimize your operation based on that. That's a day ahead market. So if you can understand that behavior of the fluctuation of the price, you can take advantage, because in certain markets, you might even get negative electricity pricing. You basically are being paid to consume electricity because the generation during the day is very, very high, because your installed capacity of solar is very, very high. So to take advantage of those makes these kind of non-conventional storage and utilization of energy much more affordable. And that's the deal between affordability and availability. What Shell is working on is a project or a family of projects which is called fully integrated thermal storage, or FITS in short. Right? You can provide heat energy in any form you like, but let's say it's in the form of steam, because steam is what we require in Shell's assets for our processes, and we want to decarbonize that. What we would require ideally is, say we have electricity available for 8 hours of the day. Say we have a solar plant and we're getting electricity from there. We have electricity available for 8 hours of the day, and 16 hours of the day we don't have access to electricity. We have to somehow store it in between and make sure that the steam supply is, say, at a constant pace, right? Of course, you can have some fluctuation in the steam supply that you require, but what the point is, you can, if you have a thermal energy storage in between, you can decouple what you require in the output to what input you have, in the sense what availability and affordability of electricity you can have. Also, another example would be if you have, say, electricity available only for some pockets in the day, maybe you're taking it from the grid and it's only affordable for some parts of the day, then also you can make sure that you maintain the supply. And of course, if you can tolerate, in the sense your thermal energy storage can tolerate a higher intermittency, then you will be able to make it more affordable. Because there would be some pockets during the day, even if it's coming from grid or renewable energy sources, that the electricity price would be much lower than its average. You need to have 3 components, of course, to such an integrated thermal energy storage. First, you need to convert that electricity into heat very, very effectively, which can again have a very high efficiency. The second one would be to store the energy, thermal energy, in the form of heat. And lastly, some kind of a heat exchanger to convert it into, transfer it to any other fluid you want. So for example, steam in this case, or even hot oil or something else. Now the conversion of electricity to heat is pretty straightforward, resistive heating and those kind of stuff, which is well known, right? Your water heater, for example. And the conversion of heat, one form of heat into, say, steam or other, is also very common. You can have a shell and tube type of heat exchanger, some other heat exchanger that is, very, very prevalent in the market now. But what about the storage part? The storage part, quite intuitively, can be from 2 type of things, right? Sensible heat and latent heat. Just for the advantage of the audience, let's say what sensible heat would mean. Just by the term, sensible means you can sense it. It means basically if you have a storage material, if you put a thermometer in there, you will be able to sense the increase in heat with the increase in temperature. Whereas for the latent heat, because it is hidden, it is latent, you won't be able to do that. But for the same temperature range, you'll be able to store a lot more energy because of the latent heat that is absorbed. So it makes it high energy density, and I think you must have heard this term like a lot these last 2.5 days. So those are the two categories. Now I would like to show you 3 of the technologies that Shell is interested in to decarbonize its own assets in terms of steam or heat demand. First and foremost, I'd like to talk about 2-tank molten salt as a thermal energy storage. It is a sensible heat based system, and molten salt is the storage material, let's say, or storage medium. As you see, there are 2 big tanks. So on the right hand side, it's a schematic representation, visualization of the system, where you have 2 big tanks. One is hot tank and one is cold tank. And of course, hot obviously means that molten salt is in a hot temperature range. What it allows is that when you need heat, when you need steam, you pass that hot molten salt and lets it pass through the heat exchanger and generate green steam. The heating part, actually, this whole concept is not new. It takes inspiration from concentrated solar power plants, where you have hundreds and hundreds of mirrors pointing the solar energy to one tower, and the tower actually inside the tower there's molten salt flowing in and getting heated and stored. So here, rather than getting the heat from the solar energy, which is again intermittent, you make sure that you have a heat exchanger or an electric heater, wherein you can heat the molten salt on demand. So that's the difference. Again, one thing that is very critical in order to make the thermal energy storage reliable and affordable is to have some kind of a market-informed guidance system. And why is that? Again, going back to the intermittency aspect of things, you might be getting your electricity from multiple sources, whether it's renewable energy or it's from the grid. And in the renewable energy, intermittency is obvious, but even from grid, like I said, the price fluctuations are so much that you want to make sure you absorb the electricity from grid only at certain times of the day. And all of that together, based on the pricing data, it has to be a very active control of when do you use your e-heater to charge your thermal energy storage. So this market-informed guidance system is a must, doesn't matter what your thermal energy storage is. Here the medium is molten salt, so it's in the form of a fluid and sensible heat. The next one I'm going to show you is solid state modular solution. As the name suggests, the medium of energy storage is solid, and it's sort of a box kind of thing where you can add modules in it, like a battery pack kind of thing. And then you can actually heat that up electrically and then pass some kind of fluid, say air, through the solid material, and then heat the air up, which can again be used for heating and generating steam or heating a hot oil or whatever. The advantage, of course, is that since it's solid, you don't have to worry about the heavy duty pumps that you required in the molten salt design, and at the same time it can be much more modular in terms of size and shape and safety and security, all of that. Of course, the market-informed guidance systems remains there, because again, you're absorbing electricity at the most cheapest that you can find it. Lastly, I would like to show this one, which is going a step beyond, where the medium remains solid, but you also taking advantage of the latent heat. So it's actually the phase change material, which is proprietary to Shell. And due to IP constraints, we can't tell you the exact combination of that PCM. But the idea is that you have the phase change material enclosed in something which you can store in the form of just any cold storage or any kind of storage unit that you see passing on a highway, something similar which is not actually catching fire or something like that. But the idea is that you have some kind of an informed system which gives you electricity. You convert that electricity into heat, store it in the form of not only sensible heat but also latent heat, and then provide green steam on demand. Of course, it's much more cheaper, and I'll just flash this slide. I mean, we have talked about this, but in principle, the need of the hour is to go from right to left, where you make sure your steam generation or your heat demand is met by the thermal energy storage directly, rather than converting again and again and again. with this, I'd like to thank you, and yeah, later if you have any questions. Thank you so much.
Thanks, Abhiti. Basically, empowering India's energy landscape. For that, she has presented her disruptive thoughts, basically, and has brought the attention of the group also on thermal energy storage. In fact, she said about 3 solutions also. It was nice and insightful presentation for the industry. Yes. We will go to the next topic, which is again different and diversified. It is on, we talk about carbon sequestration. Now, our Professor Ashutosh Kumar from Indian Institute of Technology, Indian School of Mines, is here to present on reliable estimation of carbon dioxide storage capacity in geological structures of India. Over to Mr. Professor Ashutosh. All the best.
Good afternoon. Today's topic about CO2 sequestration, particularly in geological formations of India. CO2 has become so much kind of victim guy that everybody is talking about capturing it. And after capturing it, people think of what to do. So there is option of converting it to something or burying it. So today I am going to talk about how we can bury it and where we can bury it and how much we can bury it. So there are 4 types of geological formations shown here. Number 1 is the saline aquifers. Then we have 2 the hydrocarbon reservoirs. Then we have third one. We have CVMs. And then 4th one is basaltic, formations. So particularly, then question is, do we have any estimate of the CO2 sequestration in geological formations in India or not? We have. I think from 2000 and 2022 something, we have roughly 6 presentations, 6 journal publications. 3 of them is from India and 3 from, say, international universities. Then what is wrong with all of these, journal publications or the estimates? Our perception about those estimates is that those estimates have been achieved by simply kind of thumbs rule or treating this topic in a very simplistic manner. And that's the reason that these estimates cannot be relied on. And it's not that what I am going to say you today, or based on in our work, is something that it was not present, or the way was not present, methodology was not present maybe 5 years back, 10 years back. It was present even those times, but it was not done in a proper way. Third point is that what I am going to tell you about estimates is again not reliable. But certainly, it is having better reliability than what the previous journal publications say. So one by one, we will go there and see how it has been done. What is wrong with it? So saline aquifers. The way it has been calculated is a very simple formula. Very simple formula, it's kind of you calculate the pore volume and then you multiply that by efficiency of CO2 sequestration in it. Now question is that saline aquifers are located at different depths, basically means at different pressure and temperature conditions. What will happen to CO2 sequestration efficiency? In general, and the work that has been presented by the guy, the Vikram et al. 2021. So what it assumes that it keeps on increasing. In 2018, there is one presentation, the work from Igloo. What it says, and that is very interesting, and that, that is the kind of very interesting part of this presentation. What it says that around, as we go deeper, pressure, temperature, condition changes at 2400 something depth, because of the wettability angle reversal, capillary pressure will turn negative, and what will happen that all the CO2 that we injected will leak through the cap rock. So virtually we cannot store CO2 at a depth greater than 2400. Okay. They presented the wettability angle as the linear function of the depth. And we know that wettability angle has relevance between the range of 0 to 180 degree. What happens beyond that, we cannot say anything about that. So if you see that here, can we store CO2 beyond 2400 or not? So what we did, we went with some kind of simulation work. If you see, this is kind of reservoir saline aquifers we assume. And what we did, we tried to represent various functions which can play its role in this simulation, like porosity, permeability, three-phase, relative permeability, then compressibility, density, capillary pressure, then temperature, pressure, and capillary hysteresis, all these, how it will change with respect to the depth. And then we use the CMG simulator to see how it works. So you can see that up to, say, we did up to 2400, certainly there is a leakage of the reservoir, leakage of the CO2 that we have injected in the CO2. And then on the second figure you see that shows the CO2 storing efficiency. So it's a kg per meter cube of the pore value. Now up to the point 2400, if we keep on going, neither the original author, Ms. Igloo, talks about what happens beyond that. But it is true that CO2 will keep on being stored at deeper reservoir, because as the pressure temperature changes with increasing depth, CO2 density keeps on increasing, brine density keeps on decreasing. At certain point, what we will see that something like this. Okay? So let me, So as long when pressure is low enough, where CO2 can be in the gaseous phase and low density, it tries to rise towards the cap rock, and when pressure increases, it becomes high enough that density of CO2 is higher, in comparable to the saline, water. It starts going down and it sets. In this case, you don't require any cap rock. whatever you inject, it will be stored without any cap rock. But what happens, this kind of situation, you find only at depth of somewhere around 12,000 meter. So keeping in all this view, what we understand that CO2 storing capacity, CO2 leakage, in fact, it will change. Around 200, the efficiency is 100%, so there won't be further leakage. So the leakage rate can be represented by this graph. So using this, what we have found that the saline aquifer that we can hold CO2, it is around 2270 gigaton. That is huge capacity. That is roughly around 6 times the previous authors have put up it. And the important part is that the previous authors, when they worked, they didn't even include the correct density for CO2 at a different pressure temperature condition with increasing depth. When we try to put up the correct one, so it is around 426. That is a big increase from the previous estimate. So that shows the including kind of technical calculation, simulation software, and various aspects that can affect the CO2 storage capacity estimation. Then we are talking about, I am talking about how the sedimentary basins of India. So we can see here, these are the different locations where the authors put up the estimate of 3.4 gigaton, and how they calculate is that, so there is original oil in place, and CO2 is used in the miscible gas injection process, and the recovery is somewhere between 10 to 20%, and that 10% wall recovery is equated with the CO2 storage capacity. With that, they come up with the number 3.4 gigaton. But question is that, is it really the miscible process that can store the CO2? No, there are various aspects in which you can consider storing CO2. The 10% recovery is considered when we consider CO2 a very costly item, and we cannot go beyond certain injection capacity. So we did some kind of simulation work, and we came with the estimates that, you see here, yeah, it can be around, so our some simulation work shows that around 600 billion barrel of oil production from miscible CO2 with PV pore volume CO2 injection resulting in 100 million metric ton, and that shows that our, I think this in the last slide. So we will show the estimate. In this CBM case, our simulation work shows what happens in CBM. CBM, the original authors, what they did, they calculated the volume of methane that is present in these CBMs, and they estimated that one volume of CH4 is equivalent to around 2 to 3 volume of CO2 that can be stored here. And based on that, they came up with the certain numbers. But here again, when we have CO2, there are two options. So when you inject CO2 in CBM reservoirs, certain amount of CO2 keep on increasing with the produced CH4. At 12% around you stop. So when you stop injection, you can still keep on producing the CH4, or you can stop producing and keep on injecting CO2. So there are two cases, and when we did some kind of simulation work, we came up with the estimates of around So what we have seen that in both cases, the second case, when we continue with CO2 injection and stop production of methane, results in the larger storage of CH4, and the two graphs shows that. Then the last one, the basaltic CO2 sequestration in basaltic formation. Our colleague has presented this in some other session in details with this simulation work, and what they have found that there are two basins, like one Rajmal basin, Deccan volcanic province, where we can store the CO2, and you can see the figure in the Deccan basin, we can have 381 gigaton. In case of Rajmahal, we can be 680 ton. And compared to the Vishal Ital Vikram's work. So here is the summary. So saline aquifers, it is around, our projection is around 2,000 something. And even if you reduce half of it, so it's 1,062 something. I am saying this because the work is not comprehensive work. It requires lot many of consideration. What I presented is just a small part of the technical calculation or technical aspect that must be included in reaching some kind of estimate. In the EOR reservoirs, it is around the current one is 2.23. Okay. That we have found. And in case of ECBM, it is 5.3 gigaton, and in basaltic formation, it is around 380.6 gigaton. So I think I would just add, couple of sentences, because this presentation doesn't, show the entire amount of, technical considerations and the simulation work, modeling work, experimental work that are needed to present a reliable number. So what I want to say that we are working on this. So whoever wants to work in this area, they must work on this modeling aspect and supported by some experimental work. Merely by using some kind of smaller formula or some kind of thumbs rule, that it is 10%, 2%, presents a very weak number, and reliability is certainly questionable. You can add the reliability. Again, what I have presented, this is also not reliable. This is just, one step ahead or much better than the previous one. It's there. So it's the, proper considerations of all these aspects must be given when reaching a certain number as estimates. Thank you very much.
Thank you, Professor. Basically, it's really surprising that various test results, when you consider flow dynamics, so the estimations may change so variably. So it's very interesting study, and it is very good topic, how, where, and how much to bury CO2, because the topic is very relevant in the current context of carbon sequestration. Very wonderfully researched and presented. Thanks, Professor. Now we come to the end of this session on long duration energy storage solutions. If the audience have any questions, they can meet the speakers directly, and since paucity of time, they can meet the speakers directly and they can interact. Thank you very much.